So yeah, as you might be aware, I record all these sessions. So if you miss them, if whatever you want to go back and watch them, they're on here. Um, Here I've just included the QR code for the attendance form. So feel free to sign that. This is a different attendance form to last week's one. So this is like week 2 attendance. Yeah, on the right, it's my notes. I'll scroll down a little bit as well. These are the recordings. You can actually also find this QR code through my notes. So if you ever need to find that, yeah, where the recordings are, that's where they are. In terms of our lesson plan, right, we're gonna run through moments, and then we'll talk about structures. Let me zoom in a little bit more. Structures, supports, and then I'll quiz you guys. And then we'll have a break, and then I'll go through 4 questions. How does that sound? So I think this week won't take too long either, just like last week. I think from weeks 3 and 4, the course does speed up a little bit, so just keep that in mind. I think you tackle beams first and then trusses. Could be the other order, but we're going to learn about both of those, and then in the week 5 tutorial, correct if I'm wrong, but the quiz is in the workshop, right? Or is that not true anymore? That's how it worked last year. I haven't checked this year.
I know there are quizzes, but I think they're just weekly.
Oh, there's no midterms?
There's also, no.
So the quizzes are embedded in the workshop in week 5 and 9, right? Because that's how it ran last year. I'm not sure how it runs this year. These are like midterms. There was one last year for statics and then one for dynamics. Yeah, look, that's pretty far away still, but I'll have another check of the assessment outline just so I can help prepare you guys for those if they are still part of the course. But yeah. I see a few people just still scanning, so I'll just leave this up for a second. Okay, I want to quickly correct a little mistake I made last week. It's nothing that I wrote down, but it's just something that I said, and you might see it in the recording. I don't want you guys to get the wrong idea. So in the last question, when we were talking about friction, I just briefly said something which I realized was wrong, which is that when you have enough pulling force and then you're in motion, that's correct, but the sum of the forces doesn't necessarily equal 0 in that case. I said it was still in static equilibrium, but when the box starts moving, the force is equal to mass times acceleration. We'll learn more about that in dynamics. That part's true. The only time when the box will be moving, but in static equilibrium, is when the driving force, so that here's the tension force, if you remember, is that tension force, the horizontal component of that, minus the kinetic friction. If those two balance each other out exactly, that means that you have a constant velocity and 0 acceleration, right? Makes sense. That's a special case of static equilibrium, but in motion. It's kind of, you can think of it like, even though we're on a planet which is accelerating, which is just like moving through the galaxy, all that stuff, yeah. Since we're like moving at a constant velocity, that kind of thing, yeah, there's no acceleration due to like all those things. Yeah, I don't know. Hope that makes sense. Yeah, any questions on this part from last week? Okay, if not, we'll continue on with the content which we're going to go through this week, right? So I'm going to show this every lesson. This is just that original tree diagram which I drew up last week, but you'll see that the structure we can kind of highlight along where we are. So this week we're going to be talking, we're going to continue on from the basics essentially, right? Where we primarily want to talk about the moments. Last week was, if you remember, it was just the forces. We'll also briefly touch upon structures. We're going to talk about it fairly generally. We're not going to talk, we'll talk about beams, but we won't really be talking about trusses or frames just yet. But you're going to see a bunch of different structures in the practice questions here. Okay, makes sense so far? Cool. So here's a new tree diagram. We're talking about moments. So You might be familiar with this if you've done engineering studies in high school, or if you're up to date with the lectures. But if you just did physics, like the Physics 1A course, you might not be too familiar with the concept of moment yet. So there's a few components to this, but it's pretty critical to the basics of how this course will work, right? So first, let's talk about the types of moments. You're going to have bending moments, and you're also going to have torque, right? They're essentially different, like they're essentially the same phenomenon, but happening kind of in a different perspective, if that makes sense. Okay. So again, we're going to get a little bit theoretical here, but if we have something that's on an axis, I'm just going to draw it as a dotted line. This could be a rod. This could be a beam, right? We call that imaginary line that runs through the center of that the axis. And so when we talk about axial forces like tension, that's what I'm referring to. Forces which act along that kind of direction, right? So I suppose torque is a little bit more intuitive. If we're talking about this nut that we tighten, right? The axis is running through that way, right? And so if you have a twisting around the axis like this, that's called torsion. It's called torque. And in terms of the formula will be the same as when we're talking about bending moments, which will be the focus of this course. We're not going to be talking about torsion very much in this course, but yeah. Okay, in contrast to that, if we have, again, like a rod, like a beam or whatever, and it bends like this, right? So it would deform like this, it would sag in this case, right? This is called a bending moment, right? And this can be due to moments which I've shown like this. It can also be due to when you apply shear forces. Shear forces are act perpendicular to, suppose like, yeah, shear forces will act perpendicular to this axis, right? And so that force, you can just kind of see, will produce some sort of moment. Yeah, I don't want to overcook the explanation of that just yet. We're going to get into what bending moment diagrams and stuff look like next week, I think, or the week after. Okay. Formulas. The formula is literally so easy, you won't need to write it down like in any kind of cheat sheet that you're going to bring into the finals or whatever like that. It should just be something that you can just recall in your head. It's going to be, so this is called, well, this would be bending moment, right? Is equal to the force, so, multiplied by this. This is called the lever arm. All right. I'll explain what the lever arm is in the diagram I have on the next page a little bit more. But sometimes this lever arm is denoted with R or something like that as well. So it's kind of interchangeable. Yeah. In terms of its units, right? So if you see the actual physical variables that we're multiplying together, you can kind of guess that it's going to be a force unit multiplied by a distance unit of some sort. The lever arm, you can think of it like a perpendicular distance. So it's some sort of distance, right? I'll explain what the perpendicular part means a little bit more on the next page. But just, I guess, like conventionally, right? Newton meters, you'll see these kind of units for machines, generally, relatively small scale things, right? So these are for like machines. What else I've written here? Sure. Some smaller machines might use Newton meters, but especially in the civil stream, right? You're going to see this used for big things like buildings, beams, trusses, all these structures, right? We're gonna be using kilonewton meters generally, which might seem a little bit unusual at first because they're not SI units, but they just tend to give like nicer numbers under like 1,000-ish. So they just look a little nicer, yeah, rather than like 100,000 Newton meters or something like that, right? Okay. Here's the weird part. So moments, they're actually directional, just like how forces are directional, but instead of a linear direction, actually there is a linear direction for it, but it's in and out of the page. Instead, we talk about it in terms of counterclockwise and clockwise. Okay, counterclockwise and clockwise. It's because it's that whole twisting. So that arrow that I'm drawing is like kind of a curved arrow, and it can be either clockwise or counterclockwise. Yeah. If you remember in physics, you might have done something which involved like a right-hand rule. That's what I'm talking about in and out of the page. You can correspond the counterclockwise, clockwise thing with that, but that's not a problem until you reach the last topic in this course, so don't worry about that yet. If we're looking at everything in terms of 2D, all you need to know is counterclockwise or clockwise. Anyway, counterclockwise is our conventional positive notation. Okay. Right. So if you see a moment which is clockwise, that's actually going to be negative, right? Makes sense. I'm going to take off my jacket. All right. So here's what we have. We have something here. Oh, sorry. Before I jump ahead, do we have any questions related to anything I just said there? All right. So I'm going to explain quite a few concepts at once here, but I'm going to try to illustrate it with a relatively simple example. This is what we call a simply supported beam. All right. So this is that line essentially, right? And we have a few elements here that's happening. Generally, we call this dimension L. L will be your longest dimension. It's also sometimes called the span of a beam. So if you ever see that word, it responds to that dimension, right? Usually in meters. Okay, next we have a force, right? This in particular is called a point force. It's where it's acting on a single point. That's this point here along the beam, right? Yes. Okay. And then next we have a bunch of we have supports on either side of them. So I've labeled them A and B here. They can be labeled A, B, C, D, whatever, right? Generally with a letter, right? So this support on the left and how I've drawn it, there's a few different ways you're going to see this drawn, right? But essentially what's happened is, if you remember last week, I talked about the idea of a support is something that is fixed in a particular. Okay, so this is called a pin support, right? And it has fixed translation. That means we just assume it won't move up and down or left and right. Okay, so let me just write that down. It's called a pin support. And how we notate it generally is like this: AY, AX. These represent unknown reactions acting on the support, right? And one of them is going to be perpendicular to your surface, and one's going to be axial or tangential to your surface, right? Okay, got it? Yes, okay. But this has a pin on it. That's important to remember. And so the beam is free to rotate. It's just not free to move. That's what we're trying to represent with the pin support. Yeah. So here, on the right, we have something called a roller support. Okay. This is a roller support. Someone want to guess what this does? Yes, very good. So it essentially can resist just the normal forces, right? The normal forces is the surface here, that's perpendicular, right? But it can freely move left and right. That's the tangential axis, okay, to that surface. And it's free to rotate as well. This is also a pin. I might just draw like a zoomed in version of this, right? So that's your beam or whatever. That's some sort of pin, right? If you want to look at it in like 3D, whatever, it's kind of, might look something like that, and those are wheels. It's like, imagine it like skateboard wheels or something like that, whatever, right? These are kind of abstract simplifications of what potentially like a few things could look like in real life. So if you look up different types of supports online, you might see even different types. You might see like, what's it called? Something in a slot that can freely slide around. That's still like a roller support, essentially, or a roller connection, which we'll talk about in one of the following weeks. But they all can be boiled down to these two types, or there's a third type as well, which I'll talk about next week, called a fixed support. Okay. Yeah, mathematically, there's only three types, essentially. Yeah. All right. Sorry, we're still going. So, basically, say I wanted to solve this beam, right? I know we don't really have the numbers of the forces and these like distances and whatever, but let's pretend we do. So let's pretend we know what F is, we know what D is, and we know what L is. That D, by the way, is just the distance from the left-hand side of the beam to where our point load is happening, right? Just pretend we had all these things, right? Using equations of equilibrium, right, we can actually do something here to solve for these unknowns that I've just talked about. AX, AY, oh sorry, that's called BY. So that B represents where it is, the node, and Y is just representing that direction, which is the unknown reaction. Yeah, is everyone following along? Okay, cool. Okay, basically, what I'm going to do is take the sum of the moments. This is another type of, do you remember how we did sum of the forces is equal to 0 last week? We can take the sum of the moments is equal to 0, right? But the catch here is the positive direction we have to specify as counterclockwise or clockwise. Generally, we take it as counterclockwise, right? So, counterclockwise arrow. The other thing about taking the sum of the moments is we have to choose a point that we're taking as a reference point when we're taking the sum of the moments, right? Okay, let's talk about lines of action. So for every force that you see, every force, this is a point load. This is like an external load of some sort, and we also have these reactions which happen at these points. So these are also forces, essentially, right? They have something called a line of action. So this is like an invisible line that spans infinitely in both directions of that arrow. Okay, so the line of action here for these look like this, right? So this is the line of action for that point load, right? So write that down quickly. Sometimes you'll see this as LOA. Okay, that means that I guess like mathematically, as long as we have that magnitude, the position of where I draw that arrow doesn't exactly matter. So it makes more sense for the reaction. So for this reaction, right, I could have drawn it like that, or I could draw it like that as well. And mathematically, it's the same thing, right? What I'm saying is that it's originating from this point, and it follows this line of action, right? Okay, why this is important is because it will help to inform you where to take the sum of the moments about, okay? So each of these forces, when we're analyzing the moments, we have to think about their perpendicular distances or the lever arms that they'll cause, right? So remember that F is known, right? We have three unknowns. We have AX, AY, and BY. And if we want to choose a point along this beam, right, to take the sum of the moments, where would you take it about in order to solve for one of these unknown reactions? Okay. Sorry? You could take it about A, 100% correct. There's actually another point you can take it about, it's fine. The reason is, you can take about A, which is correct, because now we're only analyzing that moment and that moment, right? So we'll only have this one unknown, which is BY. But it's perfectly fine to also take it about B. And that's because this line of action extends across like that as well. So that will eliminate two of our unknowns. Got it? So we'll only have this unknown if we take it about B going that way, and then this force will be acting counterclockwise, right? So, yeah, let's just say we'll take it about, what have I done? A. So, sum of the force about A is equal to 0, right? So, in terms of, so we're taking the sum about here, so we're talking about this moment and this moment now, right? Let's look at B first, right? Is this going to cause a positive or negative moment? Have a think about that for a second, about point A. So it's going counterclockwise relative to A, right? That's going to be a positive moment. Got it? So I'm just going to leave that without a negative at the front. And what I've done is I've just written the force multiplied by that perpendicular distance. So let's talk about perpendicular properly now. So I'm talking about this point relative to this line of action. So it's a perpendicular distance. That's the lever arm. That's what I mean by perpendicular, yeah? Okay, that's correct so far, but we also have to account for this point load now, right? So is that going to cause a positive or negative moment about A? This one's negative, right? Because it's going clockwise now relative to A. So these are the things you're going to have to think about. If you're not used to it, it's going to be a little bit unusual because you probably haven't had to do anything like this yet in physics. But in engineering mechanics, you do this all the time. So hopefully you do enough practice, it becomes second nature to figure out which one's positive, which one's negative, what the perpendicular distance is. It comes with a lot of practice. And yeah, I guarantee if you do enough practice, this stuff will be fairly intuitive. Okay, anyway. So now I'm just saying minus F, which is our point load, multiplied by D. D is that perpendicular distance that I've just named. Let's say we know that. Let's say that's 1 meter or something like that. Multiply that together. And if we solve for that, we move, because this is all equal to 0, we can just solve for By at that point and then figure out what that unknown is. Does anyone have any questions so far? Okay. Yeah, so you'll find that after you do the sum of the moments about either A or B, let's say we take it about A, you're going to know what By is, and then we can actually, instead of doing the sum of the moments about B, because that's a little bit harder to compute, we can just do some of the forces in the y direction, right? Because we'll only have one unknown in the y direction. Then we can solve for what that unknown is, right? And then we can also do the sum of the forces in the horizontal direction, which we'll find. That's how you solve for AX. So I'm talking about this kind of without writing it down because you'll see how it plays out when I'm doing the questions, right? But yeah, that's the general steps. Yeah. Okay. Okay, we'll just move on. Does everyone have any questions so far? Okay. So that covers supports, lever arms, and lines of action on a simply supported beam. Sorry, there's a ton of terminology you're gonna have to pick up pretty quickly just between those things. But yeah. Oh, before I do that, we'll give you a quiz. Yep. So if you can whip out your phone, this is just like a bit of fun, to be honest. If you want to take a break during this time, have an extended break, but we'll do a break right after I do this quiz anyway. So yeah, just humor me for a second here and do that quiz. And this should give you a little bit of a way to test your knowledge. There's no consequences for getting this wrong. Holy shit, that's loud. There's no consequences for getting this wrong, so you might as well get this wrong instead of something in the exam, you know what I mean? Okay. anyone still joining? Okay. Anyone still trying to log in? Alright, I'm gonna start it, yeah? 3, 2, 1. Look. I haven't taught you question 2 properly, but just have to think about maybe like 5 more seconds. Yeah, 5 more seconds from now. These people. Job. Okay, let's review the questions. Okay, so this is kind of a stupid question, but basically I just want to think about like this random made-up scenario I made. So if you have, so this is from top down, right? You can pretend that that hinge on the door is like some sort of hinge support, so it's free to rotate, right? But it's fixed, it's not going to move laterally. The door, from looking at it top down, is going to look like some sort of beam or rod, right? So if you have a heavy barrel, right? So doorknobs, right? Have some sort of heavy barrel, right? That's going to resist any kind of external forces which are applied to that door. Let's say it's a bunch of them. This is going to give a bigger distance to resist any of these loads from the zombies on the side, right? Then this, because the side closest to the hinge would give you less of the run, right? And so, yeah. Okay. So this is kind of the troll question, because this is actually a part of the following course, but we touched a little bit on it still in week 5 or 7 in Way's course, because it relates a lot to how civil engineers think about structures, right? These are actually, this is to do with geometric properties. So if you have a 2x4 wood, that just means the ratio is like 2 to 4, right? Essentially, it's in inches, but like, it cares about inches, right? And then, yeah. Basically, if you orientate it, this is its cross section. If you orientate it with the depth, right? Yeah, with that longer cross sectional dimension, it's going to have a better resistance against bending than if you did it the other way around. If you think about it in real life, if you were to jump on a plank of wood over like this is like a plank of wood that was bridging a gap of some sort, and you jumped in the middle, and the plank of wood is like that, it's probably going to break. But if you do it this way, it probably won't break. So these are to do with material properties, to do with geometric properties. You get into it in the following course. But there is a teaser about it, I think around week 5 in this course. Yeah, I just wanted you to think about bending. This is to do with kind of like, we're thinking about it in terms of the external forces of bending rather than the internal material and geometric properties. But yeah, okay, sorry, that was a little bit of an irrelevant question. Okay. A fixed support. So, sorry, I only briefly alluded to what a fixed support was. So we talked about a pin support, which might look like that. Talked about a roller support, it's like that, right? We also have a third type, it's a fixed support. These types of supports resist the rotation that I was talking about, as well as your translation. So in terms of its reactions, let's call that point A. We would actually have 3 unknowns to do with it, right? So you would have 3 unknowns. And so an example of this would be like a diving board. Yeah, I won't draw a diving board out. You guys know what a diving board is, right? Yeah, okay. Yes, so I just wanted you guys to understand the 3 types of supports that you can see in this course. Okay, yeah, we talked about torque and torsion, right? Essentially, the wheels in a car which is moving, right, that spins about its axis, right, which is rotating. Sorry, I'm running out of board space. That's its axis, right? So it's spinning like that. That's torsion. That's a torsional moment. But a beam, this is a bending moment. So these fall under the umbrella of moments, but they aren't the same thing as torsion, right? It's to do with relative to that axis, how it bends, how the moments are, basically. Does anyone have questions so far, by the way? I feel like I haven't answered any questions so far. Okay, anyway. A tightrope, it falls under a similar case as the bending. Yes, maybe. Okay. And then a stretched steel cable, and if you twist it, right, that's torsion for the same reason. It's just the wheel, because it goes around the axis like that. Okay. Cool. So I'll give you guys a break until 5 to 10 minute break. I'll just figure out when is a good time to go off the break. But yeah, you guys can just chat, chill, get some water, go to the bathroom, all good. Continue soon. Okay. I think now's a good time to continue. So, yeah. Okay. Basically, all I've done here is I've formally written out pin support, roller support, fixed support a little bit better, and in terms of their rules, like what they abide by. Yeah. Does anyone have any questions of these 3? Sorry, I probably should have done this before you guys did the quiz, because it would have made more sense. But yeah, I realized I left that part out. Make sense? Okay, cool. Let's continue then. So we're gonna go on to do some examples. Okay. Question 1. So in terms of where you can find these questions, I pulled these from the Mech booklet again. So I just prefer the Mech booklet a little bit better in terms of the basics. We'll see how it is later in the term. I might just keep using the Mech booklet questions, but feel free to, I think in my Google Drive folder, If you want to see the solutions for the civil questions, I've uploaded the solutions to those as well there. You can use that. Sorry. Oh, mechanical engineering school. They run in term 3. It's just their questions that they have. Yeah. I actually can't share those questions with you because those ones, you get given like a physically printed out booklet if you do 1300 in that term, and it has a QR code for those questions essentially, and it links back to your student profile, and so it's like a copyright almost. Yeah, like yeah. But I can show you the questions on my page here. I just can't give you the Mech booklet or whatever, that PDF. Anyway, so what do we have here? Anyone know? Yes, bro.
Simply supported thing.
Very good.
With uniformly distributed load and then a point load as well.
Very good. So we actually talk about uniformly distributed loads a little bit more in depth next week. I'm just going to assume beams is the next week's topic. We talk about, as you were saying, the uniformly distributed load a little bit better then, but I'll give you the gist of what's going on in this question. We've talked about the point load before. We've talked about our roller supports and pin supports. If we zoom in a little bit closer, sorry, I'm just going to zoom in for a second. Do you see how this is like a rocker support? This is mathematically the same as the roller support. It's the same as the one which is on wheels. It just looks a little bit different. But it does the same things. It resists your normal force. It doesn't resist the tangential or rotation, right? It just rocks back and forth. But yeah. The other thing that you might see in this picture is that this is a box, right? And it gives you something in kilograms, right? Which you have to like translate into newtons to do anything with, essentially, right? For our moment formula, or even our forces formulas, right? So, I've just included a little units thing. So newtons is equal to kilograms times meters over second squared, whatever. Essentially, right? First, we're going to calculate. Oh, by the way, sorry, I've drawn the uniformly distributed load a little bit lazy here. I've just drawn it as like these kind of curve shapes, but what this actually is it's supposed to look like this. It's a series of downwards arrows. That's what that is, right? And I've called that W, okay? So these are like, it's basically a point load that's spread out in one dimension. It's spread out along a certain length. You'll see what I mean in a second as we calculate the magnitude of it, okay? But first we'll focus on P. We're gonna focus on what this is. Do you remember this formula, mg, right? The mass is 300 kilograms, and we know the acceleration due to gravity, which in this course will be 9.81. I'm not going to do newtons because I don't want to have to write this shit. Times. Okay. And basically this force is already acting down, right? So I'm not going to write like negative or anything like that. I'm just referring it to it by its magnitude, right? Punch that in the calculator, that gives that number, right? And what we can do, I like to keep it in kilonewtons and meters, so I'm going to convert that into kilonewtons. So we divide by 1,000. Okay, and that gives us our point load. This is an external force, essentially, right? Because what we care about is the beam, right? So that's going to be an external force to the beam. Okay, does that make sense so far? I'm going to condense this a little bit because I'm going to run out of space if I don't. Okay. Next, we're going to talk about that distributed load. So that's the one I've done in blue here. Rather, I've done it up here, right? So this is a downwards force that's spread out over a linear run of some sort. Okay. So essentially, we're told, question, that the beam has a mass of 50 kilograms per meter of length. Sorry, I probably should have explained. This is due to the self weight of the beam. Okay, this is kind of unusual for engineering mechanics because I've only seen this question account for self-weight. It is sometimes something you do have to account for in later courses, but in engine mechanics, you don't usually have a uniform distributed load for for every single beam. It's just in this particular question we just have self-weight to account for. Okay, basically it just tells us it's 50 kilograms per meter. What does that meter mean? It means for every 1 meter, it's going to weigh 50 kilograms, right? Does that make sense? So this whole beam is, how long is it? 3.6 meters, right? Does that make sense? What have I done? Yes. Okay. Basically, what I'll do, I'm actually going to keep W in kilonewtons per meter. Yep. Okay, wait. Bear with me, guys. I haven't looked at these notes in a while. Okay, we're gonna do the same thing. It's just mg, so we're gonna times that number, 50 kilograms per meter, by 9.81 meters per second squared. Right. That gives us 490.5 newtons per meter. Remember, this is different to the previous one because we're still doing everything in terms of per meter. Okay. Okay. And then I'm going to convert it to kilonewtons per meter. That's what I was referring to. So that's what we're going to run with. So essentially, when you see a distributed load, it's typical that we express it in terms of kilonewtons per meter or newtons per meter rather than a point load which just does kilonewtons or something. Yeah. So let me just write that out. It's a distributed load. In this case, it's, linear distance. Force per linear distance. Okay, what we're going to do later, you'll see in the next step, sorry, I basically jumped ahead and jumped back, is we're going to account for that, the fact that it's 3.6 meters. We're going to convert it to an equivalent point load, that's what it's called. So we'll do that in the next step, you'll see. Okay. Okay, so we're going to solve the support reactions using equations of equilibrium. I touched upon this a little bit earlier. So if you look at the system, right, we have AY, BY, BX, right? Yeah. And so we have 3 unknowns, right? So we can do a similar thing. We can either take the sum of the moments about A or B. You can't start by taking the sum of the forces in the y direction. Okay, because you're going to end up with 2 unknowns. So if you do sum of the forces first, you'll not know AY or BY. Yeah. Does that part make sense? Yeah. You got a question?
Why is the X force? Is no force horizontal?
Yeah, good question. So basically, if I rub this out, this is what a pin support looks like. And a pin support, like that door hinge or something, right? It can resist horizontal and vertical forces. Actually, the door hinge is a bad example because it's kind of like everything's flipped. Okay, don't use the door. Just focus on this pin support, essentially, right? It's going to be able to resist if the beam moves that way. It's also going to resist if the beam moves up and down, right? But what we're saying by saying that we do have these unknown reactions is to account for that. What if we had a diagonal load, right, which has that horizontal component? Bx is the reaction that's going to counteract that horizontal component, right? Does that make sense? So even though there's no horizontal loading in this case, and in fact in a lot of cases that you're going to see, you're not going to have horizontal loading on a beam. Yeah, we just have it there because you'll find when we do the sum of the forces in the x direction is equal to 0, Bx will be 0. But yeah. Sorry, say that again. Oh yeah, in this case, Bx is it's technically the tangential forces, but since we have it horizontal, since the beam is horizontal, we just call it the horizontal forces. Yeah. Yes, technically it's supposed to be the tangential forces, but yeah. If we had a beam that's like this, that's right. On an incline or something, right? If we have a beam that looks like that, it would look like that, right? Yeah. And if we look at our coordinates like xy, then these wouldn't be the same thing, right? The horizontal component wouldn't be the tangential component. So, good questions, by the way. Yes. I might just leave that there. But yeah. Okay. Cool.
Why do we consider AY and BY to be upwards all the time? Why can't it be lower, like downwards?
Nice. I was waiting for someone to ask that question, so thank you. This is one of the first questions I had when I was learning the course as well. So what we do with reactions is, since we aren't like 100% sure which way they go, we just conventionally just assume these directions, and if we get a negative number, it's actually going the other way. Yeah. So conventionally, we take all those the unknown vertical force, we just pretend that it's going upwards, and then for the horizontal force, we just pretend that it's going to the right, essentially, right? But yeah, I think. Oh, sorry, I wrote the wrong thing. Okay, I think the reason for that is because if you think about gravity goes down. Those will be the majority of your external loads, right, in real life. And so if we have reaction forces that go up, that's going to be that's going to be the direction that it normally goes anyway, right? Yeah. Cool. Any more questions at the moment? All right, cool. So we take the sum of the force about B, so I've decided to take it about here. You know? Okay. I might just move this beam down. And we've solved for P, it's 2.943 kilonewtons. And we'll solve for W. W is 0.4905 kilonewtons per meter. Yep, that's our system so far. So we're trying to look for these unknown reactions at the moment, yeah. That's usually the first step in a lot of the methods that you're going to learn in the next 2 weeks. Okay. So, since we took the moments about B, right, we're going to essentially be solving for AY, because that's the one that's going to have a non-zero perpendicular distance, right? So, let me do a couple again. Is AY going to give us a positive or negative moment about B? Negative, very good. So we have negative AY, which is the force, multiplied by, as I said earlier, this was 3.6, right? That's because, that perpendicular distance from B to A is 3.6 meters. Okay, next we're going to account for our, you know what, I'll do the point load first. Okay. So we have this point load of 2.943 kilonewtons, right? Is that going to cause a positive or negative moment about B? Positive, very good. Okay, so that one I'll do in red. I'll just type 2.943, right? Okay, that is 1.2 meters away from point B, right? That's a perpendicular distance, right, from the line of action. Okay, are we done with this line yet? No. because we haven't accounted for the self-weight of the beam, which is the blue distributed load, right? So we have to account for this. How do we account for this distributed load? So why my notation, to be honest, is it's hard to think about it in terms of this notation. I've been a bit lazy here. It helps to think of it drawn like this a bit more, because essentially you can think of the loading in terms of the axis, how far I drew this arrow, like kind of that way, as like a rectangle. Oh, sorry. Yeah, like the force axis is like up how. Okay, wait. Let me start over. Basically, this is our distributed load, right? And this axis here gives us this much, right? And then this axis here is 3.6 meters, okay? When we multiply these two things together, right, we get the equivalent point load. It's essentially the area of this rectangle. That's what I was trying to say, sorry. Yeah. So where is this point load gonna be? Yes, in the middle. It's essentially, it's kind of like center of mass. It's the center of the force. Yep, it's the location of the force, which for a rectangle, you can imagine, is in the middle, right? So that would be, I'm doing blue. Yeah, the magnitude of that is just, sorry, I've made it very messy. Okay, the magnitude will be that, and it'll be in the middle. Okay, cool. We have to find the perpendicular distance from the line of action of this equivalent point load to our point of relevance, which is point B on the right. How much should that be? 1.8? So, yes, very good. So it's the length of the beam divided by 2 in this case, right? That's 1.8. Yeah? Does this make sense, hopefully, so far? Okay, good. Essentially, once we solve for our unknown here, ay, just for the sake of conciseness, I haven't written all like the algebraic rearranging. But yeah, what you would do is you'd move ay to the other side, add up the other stuff, and divide by 3.6, right? And that would give us some number. Okay. Sorry, so messy. Oh my god. Make this a bit smaller. Okay, now we're looking at the sum of the forces next, right? Because since we've worked out ay. Now next let's work out by, yeah? That's that tiny one in the corner there. We're just thinking in terms of forces now, so this is quite easy. Anything that goes up, we're going to make it a positive magnitude. Anything that goes down, we'll make it a negative magnitude. Okay. This is the self-weight component, and this is the point load equivalent. Oh, sorry, it's down. Yeah? Okay. And then, since we know what ay is, I'm just going to replace this part. When we rearrange for by, we get that by is 2.8449 kilonewtons. Okay. If you want to do a sanity check, right, let's go back up to our original problem. ay was 1.8-ish, right, 1.86. by was 2.84, right? Is the external loading on this beam skewed towards the left or the right side? Skewed towards the right, because the point load is loaded towards the right. What this means is there's going to be a bigger reaction taken by the support on the right. So if you want to do a sanity check, that vertical component of by should be bigger than the ay one, right? Hopefully that starts to make more sense as you do more questions, but yeah. So I'm going really slow, but again, I go slow for the first question, I'll speed up, okay? All right. Here we have the last part, which is the fastest part. The only thing that we have in terms of unknowns or external loading going in the horizontal direction is just bx. So bx is equal to 0. That's it. Right? Cool. That's our question. Done. Does anyone have any questions to do with that? Okay. We will talk about distributed loads more. We'll talk about distributed loads more next week, I think. Yeah. There's going to be more types. There'll be like triangularly distributed loads and stuff like that. And then that's when you'll also have to know about the center of that force as well. But that's fine. We'll touch on that next week. Okay. I've only done one question, Lucky.
Oh.
Yeah.
Well, I had a question and I didn't know the answer. So I'll come to you for help.
Oh, really? I thought you just left early.
Oh, no, we're not done, we're done.
Okay,
Can
sure.
you go to Statics Workshop 3?
We basically have this. This is called is it trailer hitch or something? Yeah, it's a trailer hitch, right? So you got your car and everything. Passer. Okay, this is all just fluff. Basically, if you look at the free body diagram, this is like the skeleton. It looks like this, right? Basically, obviously it goes down and like all that stuff, but all we really care about is the fact that it's all rigidly connected, and this kind of distance here and this kind of distance here. So where the force is applied and relative to point O. That's all the question really calls for. So it says, as a trailer is towed in the forward direction, the force, this one, is applied as shown to the ball of a trailer hitch. Determine the moment of this force about point O. So we're going to take our, it already tells us we're going to take the sum of the forces about point O. And yeah, essentially we're grouping together. It's going to be similar to how we did, what do I call it? Force resultant or something. Yeah, how last time we did something like this. The resultant forces grouping together forces. This time we're grouping together the moments about point O. Yeah. Okay. So, if we think about this line of action, right, and the fact that it's diagonal like this, okay, the perpendicular distance to get the moment would look something like that, right? That's, you're gonna have a little bit of trouble finding the geometry for that. It's possible, I think, but it's just annoying, right? So what might you do? I actually wrote it down in the first step before. You can break down this external force into its components, right? That's like this, if you remember from last week. What about Fy, Fx, something like that, right? What this will do, if you just think about the lines of actions of these almost like sub-forces, is you can more easily determine, oh, sorry, wait, my bad. That's a really bad representation, what I just drew there. In fact, it was wrong. It's on the point of application. That's actually correct now. So the lines of actions I drew a second ago was wrong. Be more like that, right? Okay, so essentially, look more like this. Oh, it does something wrong. I've done something wrong. Okay. It's here. Surprise. Okay. So the force is applied directly to the middle of the ball. Okay. And we'll call that component Fx and that component Fy. So I've done the same thing, but the force is directly applied to the middle of the ball for whatever reason. Not on the surface, it's just in the middle, okay? So if we look at the lines of action, sorry, this is the third time doing this, but hopefully it's correct now. we can analyze the perpendicular distances more easily now, right? Because we're given these actual like bits of geometry, right? So here's the free body diagram. We're given the information that the radius of that sphere is 32 mil, but it's irrelevant actually, because the force is directly applied into the middle, right? Okay. So we can just solve for those fx and fy components using angle geometry, right? So looks like this. F is equal to 500. That's the diagonal hypotenuse. Fx is like that. Fy is like that. That's 30 degrees, right? And so to get fx, we have to take the opposite side, right? So the opposite side is do the hypotenuse multiplied by sine 30. That's 250 newtons acting to the left, right? Okay, and then next we'll do the y component. Very similar, but this time we'll do cosine. Yeah. Okay, is that all good so far? Great. All right. So now that we have fx and fy, what we're going to do is do what I said with that force and then multiply it by the perpendicular distance, and then that force multiplied by the perpendicular distance that way. We're just going to group that together. If you think about fx and fy, are they going to cause a positive or negative moment about point O? Both are positive, yeah? So when we're calculating for, it look like this, some of the moments about point O, we're going to call that resultant moment MR, right? And we're just grouping them together, right? So we're only looking at external forces. We don't care about whatever reactions happening at that hitch, whatever. Here I'm doing everything. You got to be a bit careful with these. This is newtons and these are in millimeters. I'll convert it at the end. They're both going to cause a counterclockwise spin, so we're going to make it positive. That results in this number in Newton millimeters, right? But I'm going to convert it to Newton meters. It's just a little bit cleaner than kilonewton meters in this case. So to do that, divided by 1,000, that's in Newton meters, yeah? Cool. Is that all good with everyone? Cool. That's that question. Okay. Is it? Oh. So for this question, a block placed under the head of a claw hammer, as shown, facilitates the extraction of this nail. If a 200 Newton pull on the handle is required to pull a nail, calculate the tension. So the nail is resisting this way. We'll calculate the tension T on the in the nail and a magnitude A of the force exerted by the hammerhead on the block contacting surfaces at A are sufficiently rough to prevent slipping. So basically, it's a bit of a weird question. Again, this is like what mech students and stuff will have to think about more than civil engineers for these kind of calcs. But what is that support at point A? Have a think about it. What kind of forces does it resist? What kind of what kind of forces does it resist? What kind of things does it not resist? Yep. Okay, so so if it resists translation, wait, sorry, did you say translation? Sorry, I don't mean to put you on the spot, but could you say that a bit louder? I can't hear. Horizontal translation that way? You're right about the rotational one, right? But it it's just saying like because it's sufficiently rough to prevent slipping, we assume that it doesn't move in this motion, right? But it's free to rotate. That's all. Yeah, but it's alright because this is a bit of a weird question. Essentially, it has these kind of reactions, right? And yes, in this case, it's not really about normal and tangential. What I've done is I've just called them AX, AY because it's actually a catch-all if you think about it. It just resists motions in all directions. So I mean, technically, it could have done it this way if we're talking about it in terms of normal and tangential. But I'm going to do it like this because what I'm saying is it's just supposed to resist all of the translation in general in this particular twisting motion, right? Hopefully that makes sense. Yeah. So essentially it looks like this. This is the whole system. Okay. So where are our lines of action? That's the first thing you want to think about. We have this line of action. This is like a point load, and it's acting along that line which I just drew. We have these as well, right? These are the lines of actions of our unknowns, right? So if you were to solve this question, where would you take the sum of the moments about first? Because we know that if we take it about the wrong point, we'll have too many unknowns, right? Think about the unknowns. I'm just going to raise that one for now. Where would you take it about? Very good. So if we take it about point A, that's going to leave us with one unknown, which is that unknown t, right? The thing is, technically we could have taken it about this point as well. There's not really anything stopping you except for the fact that it's going to be much harder to find the geometry than the other point, which is point A. So I would say point A is the best point to take it about in this particular case. Okay, sum of the moments, sum of the moments is equal to 0, about point A, right? That's t. We're going to do it in meters. So what I've done in my solutions, I've just converted the mil to meters straight away. So that's that. Minus 200. 200 is a nice perpendicular distance that is given us, so we don't have to do anything weird with angles. That's 0.2 meters, right? So that's where that comes from. So T, the tension, is 800 newtons. Sorry, I've done everything in newtons and millimeters in this case. Sorry. It's newtons. It's newtons and meters. Newtons and meters. Okay, for everything. All right. Next, I mean, this pretty much frees it up. We can do sum of the forces in the x direction, y direction. Either way is fine. So let's do some in the x direction first. So here, we actually do have a horizontal external load, right? So as well as our reaction, which is AX here, we have the horizontal component of 200 newtons that we have to count for. 200 cosine 20 degrees, right? If you think about this as like a big triangle, cosine is the adjacent side. Yeah, good question.
Where did 200 millimeters come from?
Sorry?
Where did 200 millimeters come from?
Oh, that's 200 newtons. Oh, 200 mils. Oh, sorry, it's given the question. That's all. Yeah, my bad. Yeah, I probably should explain that. Yeah, so that perpendicular distance in this case is just given. It's just how far along the hammer, yeah, is the force applied. Okay, AX. Basically, if you think about this force, right? This is our external force. This is the horizontal component specifically of that external force. AX we've assumed to go to the right. Yeah, this is I think the question you had before, but we're going to result in a negative number this time around. What does that mean? It means we assumed wrong, but that's fine. We can leave it as a negative number. it just means that we have to know that that reaction force is actually going to the left with a magnitude of 187.94, right? Newtons. Does that make sense? Yeah. That's how we deal with that kind of assumption. Okay. Lastly, the last equation of equilibrium that we need to do is the y. Right, AY acting up, same with the sine component of the external force. But now we also have to look at tension, the tension of the nail. Just remember that still exists. That's acting downwards, right? Minus T, that number was 800, right? So now we have AY equal to this. So AY is counteracting the downwards forces of T and subtracted by that vertical component, essentially, right? Okay, cool. So the question actually says, calculate the magnitude of the force A, and also I've just decided to calculate the direction as well for fun. Basically, we have essentially that pin support I was talking about, right? But this has its vertical component and its horizontal component. We can take this a step further and just combine that into one resultant force that's gone to some, one resultant reaction force, essentially, right? That's what the question is asking for. So let's draw it out. AX is going to the left, right? AY was going down. Was it? I think I've done something wrong. AY was going up. Okay, AY is going that way. And so our resultant force is going to look like this, right? FA, like that. So that will be FA, AX squared, AY. This is the stuff from last week's workshop. But yeah, that's just the resultant diagonal force due to the reactions. And for the lols, we'll just calculate that angle as well. This is our inverse tan rise over run. 75 degrees, basically, right? Yeah. Cool. Does that make sense to everyone? Okay, cool. We're gonna keep going then. Okay. Oh, that was our third question. Oh, cool. We're up to the last question. Great. Yeah, there's a little bit more theory. I've pulled this question from the civil pool, actually. I would say it's a fairly difficult question because there's like a few new concepts to think about. Not a few, maybe just one. But so we have this kind of weird looking structure, and there's, we'll call it a steel frame. There's this cable, BC, that has tension running through it, right? And we have it on a pin support here on the structure. And we have this, which we've never seen before. This is called a point moment. This is like a point load, but instead of a load, it's a moment acting at a specific point. So let's say it's at that point there. That's where the twisting applies. If you want to think about what causes a point moment, you can think of it maybe like, say this frame extends in and out of the page. Could be torsion or something acting on the beam connected to it, right? Does that make sense? So like it's getting twisted that way for a beam that runs in and out of the page. Sure. Okay. But yeah, cool. How do we calculate this? So first, I've drawn a free body diagram. It looks like this, right? This is just a simplified version of the structure. We have a point load acting down there. We have the point moment, as I spoke about. We have the tension in the cable, which is unknown. And we have our pin support reactions, right? Okay. So if you were to look at this problem in your midterm, or if you have a midterm, in your finals, where would you start? What would you do? Well, we know that we're looking for the support reaction. Oh, we're looking for the unknowns of some sort. That's these, right? Where would you take the moments about?
Moments around A.
Very good. Okay, just to oppose that thought is correct, but just to oppose it, what if we were like, okay, well, we can break that into t, ty, tx, whatever, right? Are there too many unknowns to solve for now? Not quite, because this is still a function of the same number, which is t. So just remember that. Just remember that even though this is acting diagonally, it's still only one unknown, right? That's what differentiates it from a pin support. Pin support actually has two independent unknowns, right? Which is the vertical direction, horizontal direction, right? So you're 100% right, Brad, but I was just playing devil's advocate. All right, we take the sum of the moments about A. It's equal to 0. Let's take what I said a step further. We're going to actually break it up into its horizontal and vertical components, right? Because it's going to help with those perpendicular distances, right? Like that distance, right? So, in terms of this is a Pythagorean triple. This is what I touched upon last lesson. How it works is for the vertical component, we take that number on the vertical side and put it over the hypotenuse, essentially, right? So 4 over 5, and then so 80% of the forces in T are going to be acting downwards, right? And then 60% of the forces acting left of T is going to be acting left, right? That makes some sense, right? Okay, good. So what we're going to do is we're going to take the sum of the moments. We'll look at that horizontal component first, and then we're going to find the lever arm. So that's that distance there, right? From that line of action, that perpendicular distance to A. Right? So see, that's 3. That's that number there. And now, move that to the left. We do the same thing in terms of taking the moments, but for the vertical component, right? So this is the line of action. We want that perpendicular distance, right? Which, if I zoom out a little, it's 1 meter. Right? I've kind of jumped ahead. Just remember that these are positive moments. Both of these components, the vertical component, the horizontal component, they'll cause a positive moment about point A. Just keep that in mind. That bit's a little bit invisible because I didn't talk about it. Because conversely, if we look at this point load next, right, that's going to give a negative moment, right? It's going to give a negative moment about point A, correct? So that's going to be negative 60. I'll just do it in blue. And that distance is 1 meter, right? Okay, what are we going to do about this point moment, right? Well, firstly, what directions is it acting in? Clockwise. So it's going to be negative, right? Cool, but what are we going to multiply it by? We don't need to multiply it by anything because it's already a moment. Its units are already kilonewton meters. Okay, so that's the trick with the point moments. You don't need to multiply it by any kind of lever arm. It's going to give the same moment no matter which point you're referencing in terms of some of the moments. Yep, question. Okay, so this leads very well into next week's topic because it will matter in next week's topic. But in this topic, it won't, because what we're doing right now is we're analyzing the entire structure, right? So when we're looking at it from the perspective of the entire structure, it looks like it does the same thing no matter what point we're looking at the moments. But what we're going to do next week is look at the internal forces along a beam, and what that might mean is, say we're only looking at this part, and we want to develop some sort of bending moment diagram. This is like a graph that graphs what the internal response is. And then we keep looking along, and we keep looking along, and that 30 kilonewton meters of point moment is only going to be introduced once we look at that section in our overall structure. Hopefully that makes sense. If it doesn't make sense, it'll make sense next week, basically. For now, when we're taking the equations of equilibrium for reactions, we always look at the entire structure. So, yeah. Does that answer your question?
Does it T equals 5? So, you just get T.
Did I? Oh, yeah, you're right. Sorry, man. Thank you. Yes. Yeah. Yeah, so we group those together, like you do algebraic, like groups the terms together or whatever for T. Solve for T. We get T is 34.62 kilonewtons. Great. So now we've worked this part out. Okay, great. Now we can do some of the forces. I'm just going to do the y direction first. The unknown is AY. And we have 4/5t to account for, but we do know the t component, that's 34. Minus because that's downwards, right? And minus 60. 60 is that point load there. Okay, great. AY is 87.69 kilonewtons. Yeah. Okay, lastly, some of the forces in the horizontal direction. There's only two things to look at this time. That's the unknown horizontal reaction and that horizontal component of the tension. Yeah. So AX 20.8 kilonewtons. Great. Okay, cool. That concludes my workshop. So you're free to leave now. If you have any more questions, feel free to come to the front. See you all next week.